Thin film problem. A glass surface is coated with a thin film and illuminated with monochromatic light at a wavelength of 500 nanometers. So here's our glass, there's the glass surface, n is equal to 1.5. Here's a thin film placed on top of it, which has an index of refraction of 1.3, and here's air with an index of refraction of 1. What is the frequency of the incident light in a vacuum, or air? Air is close enough for our purposes. What is the frequency of the light in the film? What is the speed of light in the film? What is the wavelength of light in the film? Calculate the minimum thickness of the film required to produce no reflected light. Calculate the minimum thickness of the film required to produce maximum intensity of the reflected light. What is the frequency of the incident light in a vacuum? That's the light here, right before it hits the film. Speed of light is wavelength times frequency. Divide both sides by wavelength. We find the frequency is the speed of light in a vacuum, or in air, close enough, 3 times 10 to the 8th meters per second, divided by the wavelength of this light, which is 5 times 10 to the minus 7 meters. Right, here's the conversion from nanometers to meters. So our answer is 6 times 10 to the 14th hertz. What is the frequency of the light in the film? Please don't ever get this wrong. This is an easy one, no calculations. When light goes through a different medium or media, the frequency stays the same. The speed of light will change and the wavelength of the light will change, but the frequency stays the same. What is the speed of light in the film, or the effective speed? Velocity is going to be the speed of light in a vacuum divided by the index of refraction of the material. So that's going to be 3 times 10 to the 8th meters per second divided by this 1.3 here, and you get 2.3 times 10 to the 8th meters per second. What is the wavelength of the light in the film? Similar equation to the speed of light, except this time it's the wavelength in the film is equal to the wavelength in the air or vacuum divided by the index of refraction, 500 nanometers divided by 1.3, 385 nanometers. Calculate the minimum thickness of the film required to produce no reflected light. So we're going to use the minimum equation, all right, because we want the minimum thickness, and we want no reflected light, which means we need destructive interference. And we'll select m, which is our order here, as m equals 0. That'll give us the smallest t, and that's what we're looking for, the smallest, the thinnest covering of film. Why? Because the film is probably expensive. So here's our equation, the destructive wavelength equation, 2t over m plus a half. Multiply both sides by m plus a half because we want to solve for t. And we get 2t is m plus 1/2 times lambda d. 2t is lambda d over 2 by substituting in m is equal to 0. And the thickness is lambda d over 4, or 385 nanometers divided by 4, 96 nanometers. Now, which wavelength are we using here? We're using the wavelength that we found in the film. That's going to be important in a couple slides. So this is the wavelength of the light in the film. Calculate the minimum thickness of the film required to produce maximum intensity of the reflected light. Now, if you were making sunglasses, this is not how you would do it, right? You would want most of the light to go through so you could see and just have a very minimum reflected light. So we're going to use this equation here. This is constructive interference because we want, why? A maximum. We want the thinnest covering, the thinnest film. So we're going to choose m is equal to 1. So we have 2t is equal to m lambda, constructive interference. And we choose m is equal to 1. We get this. T, the thickness is lambda over 2, 385 nanometers. And again, we're using the wavelength in the film. And we get 192.5 nanometers thickness for the thin film.